Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics. Today we are going to discuss about the module Hamilton's Principle and Lagrangian's equations, which we have, formalism of which we have discussed in the earlier unit. Now with the help of some solved examples, we will illustrate how to use the principle. And all this falls from the paper Classical Mechanics. So students, let us see what we are going to learn in this module. As I said before, formalism we have learned earlier. Now with the help of some simple assorted problems, we will learn how to choose the appropriate generalized coordinates for a specific problem. The most important thing in the application of this formalism for solving dynamical problems is to first make a judicious choice of the appropriate generalized coordinates. Having made the choice of the generalized coordinates, you will be able to write down the expression for the kinetic and potential energy in these coordinates. And once that is done, we can set up the Lagrangian's equation of motion. In order to describe the motion of a specific system by setting up the expressions for the kinetic and potential energy, it is important, as I said, to make a suitable choice of the generalized coordinates. The suitable choice depends on the degrees of freedom of the specific problem, and this should be so chosen as to render the expressions of the Lagrangian simple. Having obtained the Lagrangian, then it is straightforward to set up the equations of motion. These equations in general are difficult to solve, but for some simple cases they can be solved analytically. So let us start with some solved examples. The first example we consider is a particle which is connected by two springs on an inclined plane. So you have an inclined plane and you have a particle connected with the two springs, and the springs are fixed on the inclined plane. So the mass is connected between two identical springs or identical spring of spring constant K and of unstretched length A. Each spring is on an inclined plane. Angle of inclination of the plane is fixed, which is alpha, let us say. And once the angle of plane is fixed, you can see the problem has only 1 degree of freedom, and we choose this degree of freedom to be the position of the particle on the inclined plane. So the position of the particle along the inclined plane is chosen to be the generalized coordinate, and as I said, the problem is only 1 degree of freedom. The expressed in this generalized coordinate x, the kinetic energy is simply T is equal to half mx dot square, and the potential energy consists of two parts. The potential energy, the gravitational potential energy, and the potential energy due to the spring or the harmonic potential energy. The potential energy due to the gravitational force is simply mg times 2a minus x times sine of alpha. Alpha is the angle of inclination, and the energy stored in the springs. The two springs is, the first spring is compressed to a length of x minus a, so it's half kx minus a whole square, and the second spring is compressed to a length 2a minus x minus a, therefore its energy is half k times 2a minus x minus a whole square. So the potential energy can be written as shown, and the Lagrangian is just the difference between the kinetic and the potential energies. Equation of the mass is obtained by minimizing the potential energy, that is, by putting du by dx is equal to 0, which gives us the equilibrium position as x is equal to a plus mg by 2k sine of alpha. Having obtained the equilibrium position, we now write down the Lagrangian equation of motion. namely d dt of dl by dx dot is equal to dl by dx. Notice that in this problem, we have only one degree of freedom, which we have taken to be x along the inclined plane. So taking the partial derivative of L with respect to x dot and then taking the time derivative, we get the equation of motion as mx double dot is equal to minus 2k x minus a plus mg sine of alpha. Now we define a new coordinate which is measured from the equilibrium position. So let us define eta as equal to eta is equal to x minus a minus mg by 2k sine alpha, which means that in equilibrium eta is equal to 0. So in terms of this new variable eta, the equation of motion becomes m eta double dot is equal to minus 2k by eta, which you can recognize as the equation of a harmonic oscillator. Restoring force which has a magnitude of minus 2k. So the solution is then a sinusoidal solution with the frequency omega given by omega is equal to under root 2k by m. Now we take an example where the Lagrangian of a particle is time dependent. We consider a simple case where the particle is moving in one dimension and the Lagrangian is given by exponential minus gamma by mt multiplied by half m x dot square minus v of x. So you can see half mx dot square minus v of x. This is the Lagrangian of a particle moving in the presence of a potential Vx in one dimension, and this whole thing is multiplied by exponential minus gamma by mt, which makes the Lagrangian time dependent. Now, the partial derivative of this Lagrangian with respect to x can be easily evaluated and is equal to minus e to the power minus gamma by mt dv by dx. Likewise, the partial derivative of L with respect to x dot is equal to mx dot exponential minus gamma by mt. Now, the Lagrangian equation of motion, namely d dt of dl by dx dot is equal to dl by dx. Now we see that dl by dx dot depends on time explicitly. So the derivative of dl by dx dot with respect to time gives me exponential minus gamma by mt mx double dot minus gamma by m into m exponential minus gamma by mt x dot is equal to minus e to the power minus gamma by mt dv by dx. And we can cancel out the common factor exponential minus gamma by mt and the equation becomes mx double dot minus gamma x dot is equal to minus dv by dx, which you can recognize is the equation of a damped driven oscillator. So dv by dx is the force which is driving the oscillator and the damping force is proportional to the velocity which is minus gamma x dot. Now let us consider the problem of two identical pendulums which are joined by a spring. So you have a system of two identical pendulums which is joined by a spring whose unstretched length is a and whose spring constant is k. The problem is to set up the Lagrangian of the system and is to obtain the equations of motion. How do we proceed? So the system consists of two identical pendulums. There are two pendulums, so it has 2 degrees of freedom. These 2 degrees of freedom can be chosen to be the angles made by the two pendulums with the vertical as shown in the diagram. So in terms of these two angles, theta 1 and theta 2, we can write down the Cartesian coordinates of the two pendulums 1 and 2, that is x1 is L times sine theta 1 and y1 is L times cosine theta 1 are the Cartesian coordinates of the pendulum 1. The Cartesian coordinates of the pendulum 2 in terms of the generalized coordinate theta 2 are given by x2 is equal to L sine theta 2 and y2 is equal to L cosine theta 2. As a further example, we consider the particle on the surface of a cone. So you have a cone, a particle is moving on the surface of the cone. Since the particle is confined to the cone, it has 2 degrees of freedom. So, which are the 2 generalized coordinates we should choose? The cone is an inverted cone with half angle fixed, which is equal to alpha or whatever. So, we have to set up the Lagrangian. So, how do we choose the equation, the degrees of freedom? Let us see. Since the particle is confined, as I said, to move on the surface of the cone, it has 2 degrees of freedom. And one choice which appears immediately to simplify the problem is to choose the cylindrical coordinates r, theta and z. But with one difference, that on the surface of the coin of this cone, since the angle of the cone is fixed, all the 3 are not independent coordinates. The z can be expressed in terms of r and theta. That is, the z coordinate is equal to r cosine alpha, where alpha is the half angle of the cone. So, we have just 2 independent coordinates r and theta. So, the kinetic energy in terms of these 2 coordinates r and theta and the other coordinate z, which is a dependent coordinate which we can remove, is given by L is equal to half m r dot square plus r square theta dot square plus z dot square, and the potential energy is simply minus mgz. So, the Lagrangian can be easily set up. The kinetic energy of the problem which we are considering here of 2 identical pendulums joined by a spring is given by T is equal to half m into x1 dot square plus y1 dot square plus half m into x2 dot square plus y2 dot square, where x1 y1 and x2 y2 are the Cartesian coordinates in the plane of these 2 masses which are attached to the spring. In terms of the angle theta 1 and theta 2, we can write down the kinetic energy T as half ml square theta 1 dot square plus theta 2 dot square. The potential energy can be easily seen to be minus mgy1 minus mgy2, which is the gravitational potential energy, and the potential energy due to the spring is half k a minus x1 plus x2 minus a whole square, because the unstretched spring has length a, and the way we have defined our coordinates, you can see that the change in the length of the spring is a minus x1 plus x2 minus a. Therefore, the potential energy can be written as u is equal to minus mgl cosine theta 1 plus cosine theta 2, because y1 is equal to L cosine theta 1 and y2 is equal to L cosine theta 2 plus half KL square sine theta 1 minus sine theta 2 whole square. So, we have now this problem which is expressed, the kinetic energy and the potential energy are expressed in terms of 2 angle variables theta 1 and theta 2. The equation of motion for the particle 1 is d dt of dt by d theta 1 dot is equal to minus dt by d theta 1. We obtain very easily that theta 1 double dot is equal to minus g by L sine theta 1 plus k by m multiplied by sine of theta 1 minus theta sine of theta 2, and the whole thing multiplied by cosine theta 1. And we have a similar equation for theta 2. Now this equation for theta 1 and theta 2 are not easy to solve in general, but for small oscillations, these equations can be solved without much difficulty. As a fourth example, we consider a particle which is attached to a spring in the vertical plane and is free to move in the vertical plane which we have represented as the xy plane. The position in the vertical plane of a mass which is attached to the spring at any time is given by the angle theta. So, the Cartesian coordinates of the mass attached to the spring can be written in terms of this angle theta. The kinetic energy of the particle is clearly half m x dot square plus y dot square, and its potential energy is equal to the gravitational potential energy plus the harmonic potential energy because of this spring constant. So the potential energy U is equal to minus mgy, where we have taken the zero of the gravitational energy at the origin. So U is equal to minus mgy, minus mgy is the gravitational potential energy, and the spring energy is half k multiplied by under root x square plus y square, which is the length of the stretched spring, minus a, which is the length of the unstretched spring. Therefore, under root x square plus y square minus a is the extension in the spring, and the spring energy is then half k into extension square, which is half k into under root of x square plus y square minus a whole square. Writing x and y in terms of the polar coordinates r and theta, we can rewrite the kinetic energy as half m r dot square plus r square theta dot square, and the potential energy U equal to half k r minus a whole square minus mgr cosine theta. Therefore, the Lagrangian L is given as the difference between the kinetic energy and the potential energy, and the equations of motion are obtained from the Lagrangian equation of motions, which are degrees of freedom. So, I have two equations for in r and theta. The equation in r is given by ddt of dl by dr dot minus dl by dr is equal to 0, and for the coordinate theta is ddt of dl by d theta dot minus dl by d theta is equal to 0. Namely, the equations of motion become mr double dot is equal to mr theta dot square minus k into r minus a plus mg cosine theta, and the second equation is m ddt of r square theta dot is equal to minus mgr sine theta. And you can see these equations are not again easy to solve. Now we consider a bead which is constrained to move on a vertical circle under gravity as shown in this diagram. So we have a bead of mass m which moves on a vertical circle of radius r under gravity. We have set up the Lagrangian and the equation of motion for this problem. So the first thing is to see how many degrees of freedom does it have. Obviously, since moving on a circular path, it has only 1 degree of freedom, which we can choose to be the angle made by the radius vector from the center of the circle of the bead with the vertical. So consider the particle at a point. So this circle is in the circle is in the xz plane. So we consider the particle at a point with the Cartesian coordinate x and z on the circle. In terms of the polar coordinates r and theta, x is equal to r sine theta and z is equal to r plus r cos theta, and r is fixed. We thus have the motion described by only one coordinate theta. The kinetic energy T is a half m x dot square plus y dot square. Now writing x and y in terms of theta, the kinetic energy becomes half m r square theta dot square. So the next thing is to write the potential energy. Potential energy mgz. So potential energy is simply mgr into 1 plus cosine theta. For the motion of a particle on the surface of a cone, as we mentioned, there are only 2 degrees of freedom, and the Lagrangian then reduces to L is equal to half m into r dot square cosecant square alpha plus r square theta dot square minus mgr cotangent of alpha. That is our generalized coordinates r and theta. The coordinate z is related to r and theta, so we have removed that. The coordinate theta does not appear in the Lagrangian, because if you look at the expression for Lagrangian, the theta doesn't appear, which means theta is a cyclic variable, and therefore the momentum conjugate to the cyclic variable, namely p theta is equal to dl by d theta dot, is a momentum conjugate to the coordinate theta, is conserved. Thus, P theta is equal to mr square theta dot, which is equal to constant, and you can recognize that mr square theta dot is nothing but is like the angular momentum, L. Let's call it L. Therefore, the equation corresponding to the coordinate r is d dt of dl dr dot minus dl by dr is equal to 0, which becomes r double dot minus r sine square alpha theta dot square plus g sine alpha cos alpha is equal to 0, and we get the equation to be r double dot, that is d2r by dt square minus l square by mr cube sine square alpha theta dot square plus g sine alpha cos alpha is equal to 0. For a bead which is constrained to move on a vertical circle under gravity, having written down the kinetic and potential energy, we can easily write down the equations of motion. So, equation of motion for the coordinate theta is theta double dot is equal to g by a sine of theta, which can be written as d dt of theta dot square is equal to minus 2ga by a d dt of cosine theta, because d dt of cosine theta is minus sine theta, so the sine theta we replace by minus d dt of cosine theta, and d dt of theta dot square is twice theta dot theta double dot, and therefore is d dt of theta dot square is equal to minus 2g by a d dt of cosine theta, and this can be easily integrated, and we get theta dot square is equal to minus 2g by a cosine theta plus a constant of integration, and from this we obtain d theta by dt as under root of c minus 2g by a cosine theta. C is a constant of integration, and this can be further integrated to give t in terms of theta as time is equal to integral d theta divided by under root c minus 2g by a cosine theta plus yet another constant of integration. As a final example, we consider a charged particle in a constant electromagnetic field. So, we consider the motion of a charged particle of charge E and mass m in the presence of an electromagnetic field. We have already seen that the Lagrangian of this particle in the presence of electromagnetic field is given by half m times the kinetic energy, half m times x dot square plus y dot square plus z dot square minus E times phi plus E by c v dot a, where E is the charge of the particle, phi is the scalar potential, v is the velocity of the particle, and a is the vector potential. We know that electric and magnetic fields are obtained in terms of the scalar and vector potential by the simple relation that the magnetic field B is curl of A and the electric field E is minus gradient of the scalar potential minus the time derivative of the vector potential. Then we can obtain the Lagrangian equation. So, we have the Lagrangian, we can obtain the Lagrangian equation. But it's much easier to use the expression for the Lorentz force. Now, we know the Lorentz force, that is the force experienced by a charged particle in the presence of electric and magnetic field, is simply given by F is equal to the charge times the electric field plus 1 by c v cross b, where c is the velocity of light. And once you have the force, you can simply write down the Newton's equation of motion, which is much easier to do. While considering the motion of a charged particle in the presence of electromagnetic field, let us consider the magnetic field to be along the z-axis, and we consider the electric field in the yz plane. That is, the magnetic field B is equal to B naught into a unit vector along the z direction. So, B is along the z, and the electric vector E has a component EY along the y direction and a component Ez along the z direction. Now, V cross B can be easily evaluated, and we obtain V cross B to be a vector which is equal to B naught into Y dot is the component along the x-axis minus B naught x dot is the component along the y-axis. So V cross B is B naught Y dot unit vector along x minus B naught x dot unit vector along y. Now the equations of motion can be easily written down, and we obtain mx double dot is equal to E B naught by C Y dot, and my double dot is equal to minus E B naught by C x dot plus E times EY. The motion along the x direction is not affected by the electric field, where the motion along the y direction is affected by both the magnetic field as well as the electric field, and the motion along the z direction is only affected by the electric field component along the z direction. Motion along the z-axis can be immediately obtained by integrating the last equation twice, and we get z is equal to z naught plus z naught dot t plus half E by m Ez t square, where z naught dot is the initial velocity of the particle. If the particle starts at rest, whose coordinates then at t is equal to 0 are given by 0, 0, 0, then x naught is equal to y naught is equal to z naught, and x naught dot is equal to y naught dot is equal to z naught dot is equal to 0. Thus we have solution along the z-axis is equal to half E by m E2 t square, because particle starts from rest with at the origin. Equation along an y-axis can be solved by a trick. The trick consists in multiplying the equation x equation by I and adding it to the y equation. So we get x double dot plus iy double dot minus ie b naught by mc x dot plus iy dot plus ie by m ey. Now the last term in this equation, ie by m ey, is a constant. It does not involve the coordinate. So what we do to solve this equation, first thing is we write eb naught by mc as omega, and then we get x double dot plus y double dot is minus omega x dot plus iy dot plus ie by m ey. Now, as I mentioned before, the last term in this equation is it does not depend on the coordinates, so we define a new coordinate eta, which is x dot plus iy dot. So in terms of this new coordinate eta, the equation reduces to eta dot is equal to minus I omega eta plus ie by m ey. And this is a first order differential equation whose solution is given by eta is equal to a some constant a exponential minus I omega t plus ey by m omega. So eta in turn is equal to x dot plus iy dot. Therefore, x dot plus iy dot is equal to a times exponential minus I omega t plus e times ey divided by m omega. Now, equating the real and imaginary parts of this, we get the equation for x and y coordinates, namely x dot is equal to a cosine omega t plus ey by m omega, and likewise y dot is equal to minus a sine omega t. Now, this is a first order differential equation. We can just integrate it, and with respect to time, integration x is equal to a by omega sine omega t plus ey by m omega t, and y is equal to a by omega cosine omega t, where the integration constant is equal to 0 because of our initial conditions. So students, let us summarize what we have learned from these examples. So with the help of these specific examples, we have illustrated how to make a judicious choice of the generalized coordinates, which makes the description of the Lagrangian simple, and hence the description of the motion simple. Thank you.